All right, we're looking at 4.6, the fundamental theorem of algebra. So just to review, back in the last section, we were on 4.5, and this one I believe was called solving. Was it called solving? It was a long one. Solving, yeah. So plain old solving and the fundamental theorem, they go together. Let's look at number 35 here. Just to review how we did this problem, right? We had equals 0, right? There's our equal symbol. So that means that we're solving for our x values. And what we wanted to start off by doing is just plain old factoring. And we looked at it and we could not factor it. But if you can factor, you want to factor. We couldn't factor, so then we went to the rational roots theorem. And that's the whole P over Q, which is factors of the last term over factors of the first term. So we looked at factors of 64. Those were these top numbers here, right? The plus minus 1, 2, 4, 8, 16, 32, and 64. And then nicely, our denominator was just going to be plus or minus 1 because we had a 1 in cubed out front. So we looked at those numbers, and those numbers are given to us by the rational roots theorem. And they tell us that if the roots are rational, then they have to be listed there somehow. So we tested out some roots, and we got that -4 is a root. Then we used long division to force our polynomial to factor. So that was all over here. We were dividing, and then over here, we were able to factor it, right? In the beginning, we weren't able to factor by grouping, but what we were able to say is we could divide out by n plus 4, and n plus 4 would give a root of -4. So then we had our remainder there, the result of our division was n squared plus 8n plus 16. And then we could break that apart here using the 4 plus 4. So there was our pattern there. And if we remember, back in the very beginning of this problem, we looked at this 3. It was highlighted green there. That green 3 means that he's a degree 3 polynomial, which means he has to have 3 roots. Now, in the next section, what section is this? This is section 6. The fundamental theorem of algebra, we actually write down that rule, that a function of degree n has to have n roots. So let's read here. If f of x is a polynomial function, or a polynomial of degree n, where n is greater than 0, right? And if n was 0, then it would just be a constant, something like 0 equals 0, right? You could say that 0 is a polynomial, and he's degree 0. So we want degree to be greater than 0, so that would be something with a variable in it. So let me start again. If f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of complex numbers. And we've looked at complex numbers before. Remember that complex numbers, they contain the imaginary, the i's, and also the reals. So all of the numbers that we have ever used are contained in the complex number system. But then we also get the i's that we learned about in chapter 3, I'm thinking section 2. So there's our fundamental theorem. And then the corollary, this is the real important part here. A corollary is kind of like a side note, right? And in this situation, the side note is kind of more important than the real theorem. Let me start reading right here. If f of x is a polynomial of degree n, where n is greater than 0, then the equation of f of x equals 0 has exactly, and this is a big deal, exactly n solutions, provided each solution repeated twice is counted twice, 3 times is counted 3 times, and so on. So, in our last problem, where was he? That one that I was talking about earlier. This one right here, number 35. We started off looking for 3 solutions because we had an n cubed. And then we ended up saying, well, we have a multiplicity of 3. That's us counting the solution 3 times, so it has 3 solutions. And in the future, we're really going to want to care about that multiplicity, because like we did in the last problems, we kind of are searching for our ending, right? If we have 4 answers that we know we need to find, we have a degree 4 polynomial, then you start looking for answers, and once you get to 4, you can stop searching because you know you've found them all. So let's read this last statement here. This means that an nth degree polynomial function f has exactly n zeros. So that's a good statement there. sometimes the zeros are repeated, right? That would be like a multiplicity. All right, number 36. How many solutions does x to the fourth minus x cubed minus 64x plus 64 equals 0 have? How many solutions does it have? Well, we look at its degree. This is degree 4, so there has to be 4 solutions. There's going to be 4 solutions. Now we look for what are the solutions. And if we can, we want to factor. So I'm going to try to factor this. So if I factor by grouping, let me just rewrite it here. X to the fourth minus x cubed minus 64x plus 64 equals 0. I'm going to look at the first 2 and the last 2. I'm going to look at them separately. The first 2 I can pull out an x cubed, and I'm left with x minus 1. Now I want to pull something out of the second binomial such that I have x minus 1. And I can pull out a negative 64, and that'll work out just perfectly for us. So now I'm going to have x minus 1 out front, and then I'm going to have x cubed minus 64 equals 0. I know that x cubed minus 64, I know that can be factored. And the way that I know that is this is x cubed minus 4 cubed. And that's a difference of 2 cubes. And that, again, that's, if you remember, we have a formula for that. That's a formula that we don't normally try to memorize, or that I don't normally make people memorize. But I do want to look at it here now. Let me see if I can find the formula just really quickly. We have a cubed minus b cubed equals. This is going to be a minus b, then a squared plus 2, is it 2ab? I think it's 2ab plus b squared. Let me actually find it written down somewhere just so that I make sure that I have it right. Oh, I was wrong. This is just a plain old AB, no 2 in front of it. So there's our formula that we're using there. I'll probably write this formula up whenever we start going over this section, and you'll probably want to have it somewhere in your notes. If you want to memorize it, that'd be awesome. That'd be a good thing, but you can always just have it handy. So this means that we can have an x minus 1 there, and then we can factor into x minus 4, and then x squared plus 4x, and then plus 4 squared is 16. And this is still equal to 0. So now that we have it broken apart here, we have an x minus 1, and to me that's pretty simple. X minus 4, again, that's pretty simple. And then we have this x squared plus 4x plus 16. And it'd be awesome if we could factor that. I don't think it's going to factor, though. 16, we look for 2 numbers that multiply to be 16 and add up to be 4, and I'm just not coming up with one. So what we're going to do here is we're going to go ahead and break it apart so we can take care of the x minus 1 and the x minus 4. So we're going to say x minus 1 equals 0, x minus 4 equals 0, and then we'll have x squared plus 4x plus 16 equals 0. In the first one, we get x equals 1, then x equals 4, and I'm going to go ahead and circle those. So there's 2 solutions. We remember that there's supposed to be 4 solutions total. And in this last guy, he is quadratic because he has degree 2 right here. He has to have 2 solutions contained within it. Because I can't figure out how to factor it, I'm going to use the quadratic formula. So I'm going to pull this over here, and I'm going to say that x equals, and it's negative b, so negative 4, plus or minus the square root of b squared. This can be 4 squared minus 4 times 1 times 16 all over 2 times 1. I'll go ahead and write this right here. I'm going to type the discriminant into my calculator. That's the piece under the root. So 4 squared minus 4 times 16. That gives me negative 48. So I'm going to do negative 4 plus or minus root negative 48 all over 2. Now we can see that negative under the root. That means we're going to have an imaginary solution. So we'll go ahead and put that I there. We'll have negative 4 plus or minus I root 48 all over 2. And then we want to try to break apart the 48. That's 12 times 4. 12 is 4 times 3. And we could break apart the 4's, but I'm actually going to pause and I'm going to circle them now, and then I'll circle the 3. This means that I can rewrite this as negative 4 plus or minus 4I root, I guess it's just a 3 now, root 3 all over 2. Now the negative 4, the positive 4, and the 2, those can all reduce, and we'll just have negative 2 plus or minus 2I root 3. And that's going to be our last answer here. So let's recap our problem. Up here we said we had 4 answers. We had 4 solutions. Right here we found that x equals 1, x equals 4, and then negative 2 plus or minus, right? The plus or minus counts as 2 different solutions. So we do have 4 unique solutions. Alrighty, there was number 36. We didn't have to do any kind of division here because we were able to get it to factor. If you can't get to factor, that's when you have to resort to using the rational roots theorem and division. So let's look at 37. Find the zeros of, and then they have our function there. Check your answer with a graphing calculator. So I first want to say, well, how many solutions should I have? I should have 4 solutions. And I get that by looking at this little 4 right there, that exponent of a 4. So I count my terms. I have 1, 2, 3, 4, 5 terms, and we don't have any way to solve, to factor something with 5 terms. The longest we can go is 4 terms, and that's factoring by grouping. But this one has 5, so we don't have a good way to do that yet. So that means we're going to have to resort down to using division. I'm going to look at the rational root theorem, and I want to look for all of our possible roots. We're going to have factor 8, so plus or minus 1, plus or minus 2, plus minus 4, and then plus minus 8. And then what's nice is our first term there is just plus or minus 1. So I'm going to take out a calculator. I've got a graphing calculator right next to me, and I'm going to try out a few of these points. I'm going to actually go to the y equals, and I'm going to type in this function. So I'm going to type in x to the 4th minus 6x cubed plus 9x squared minus 6x, and then plus 8. And I'm sorry I don't have a good way to put the grapher up on the screen here. Just so you guys can kind of see what I'm looking at here. If you have a grapher, that'd be a good thing for you to look at right now. But it looks like it does something like that. So there's a solution right there and right there. And it looks like it's at x equals 2 and at x equals 4. It looks like 2 and 4. So I'm going to go to my table and I'm going to confirm that 2 and 4 do work. Yep, at 2 and 4 I get zeros. So I can make like my little T-chart. I think we did this in the other lesson. 2, 0, 4, 0. So we have 2 of our answers there. We have 2 and we have 4. Now I'm not going to write x equals 2 and x equals 4 yet though, because I still have 2 others that are missing. So that means I'm going to have to break my equation apart. So I'm going to say, well, I'm going to choose my x equals 2. That means that I have to have something like x minus 2 equals 0, right? And this would be a factor of my equation, or of my function. So I'm going to use synthetic division. No, I'm going to use long division. You know what? I'll use synthetic division. I don't think we've used that in a while. We want to find k value, and k equals 2. K always matches up with your actual root. And the 2 goes right here. And then up top, we write our coefficients. So we're going to have 1, negative 6, 9, negative 6, and 8. If you remember, synthetic division works a little bit faster than long division, but it's normally a little bit harder to actually understand what's happening, right? Long division, I think it's kind of easy to follow what's happening. Synthetic is just kind of difficult. Now, these numbers right here, I got from up here. They're the coefficients. So now, in synthetic division, you drop down the first number, 1, and then you multiply. 2 times 1 gives me 2, and then I add these. That gives me -4. Then I multiply to get -8, 1, 2, -4, -8, and then 0. This remainder being 0 confirms that x equals 2 is a good answer. So I'm going to go ahead and circle that. And what this is telling me is that my f of x that was up top, I could break it apart to say x minus 2. That's this 2 right there. And then I could have this other guy written here. And what would he be? He'd be a -4 at the end, and then 1x, -4x squared, and then 1x cubed. So we broke it apart, and then we're wanting to say that this guy is equal to 0. But what's neat, and this is something that we did the other day as well, this original function f, we could not factor him because he had 5 terms, and we don't have a way to factor 5-term polynomials. But down here, we kind of forced it to factor by using synthetic division. You could have used long division as well if you wanted to. So this gives us here that my x minus 2 equals 0, and then I have x cubed minus 4x squared plus x minus 4 equals 0. And I already took care of my x minus 2. I got my x equals 2, and I already circled that up here. Now I want to look at my other piece. Now this is a 4-term polynomial, and we do know ways to factor that. We can use probably factoring by grouping. So I'm going to look at my first 2 and my last 2. The first ones I can pull out an x squared, and I'm left with minus 4. The other ones I can just pull out a 1, and I'm left with x minus 4. So I have x minus 4, and then x squared plus 1. So I have x minus 4 equals 0, and then x squared plus 1 equals 0. On the left, I get x equals 4. And there's another solution. Right, remember, we had one solution that was up above here, the x equals 2. We've already circled him. Now we have a second solution, x equals 4. And if you remember, we're trying to get 4 solutions. So our last 2 solutions have to be in this quadratic here, the x squared plus 1 equals 0. So I subtract my 1, and I get x squared equals -1. And then I take my root. And whenever we take a root, we put in a plus or minus. And I'm going to have x equals plus or minus the square root of -1. And the square root of -1 is I. So we just have plus or minus I. And there's our answer. We have, let me highlight them, x equals 2, x equals 4, and then x equals plus or minus I. If you want to rewrite them together, that'd be fine. But if you have them separately, but you box them in like I have, that would be sufficient as well. All right, so something to make note of, something to notice, is that we had the plus or minus with the I, with the imaginary solution. We had 2 of them. They came in a pair. In our last problem that we did, we also had imaginary solutions, and he came in a pair, right? We had the plus or minus 2i root 3. And that's a theme. That's actually something that has to happen. If you have an imaginary solution, then he has to come in a pair, right? And that can go back, we can think back about the quadratic formula with this plus or minus in there. An imaginary solution has to have the plus or minus. So let's scroll down. Complex conjugates. Pairs of complex numbers of the form a plus bi and a minus bi, where b is not 0. They're going to be called complex conjugates. Remember, a conjugate means 2 binomials where the middle symbol is swapped, right? In the first one that we highlighted, there's a plus. In the second one, there's a minus. Right below it, we have the complex conjugates theorem. if f is a polynomial function with real coefficients and a plus bi is an imaginary zero, then a minus bi is also an imaginary zero. So let's look at number 38. We're supposed to write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1, and the zeros at 5 and then 1 plus I. So because we have this 1 plus I, we know that his partner, 1 minus I, also has to be there. So now we have three unique solutions. We have 5, 1 plus I, and then 1 minus I. As a factor, this would be x minus 5. Over here we'd have x minus 1 plus I, and then x minus 1 minus I. See how I wrote the 5 right there in front of, with a minus in front of him. 1 plus I had to put parentheses around him so the minus would go to both. And then 1 minus I, again, I had to use parentheses there. Now we want to distribute. And we want to distribute it until we get back to a standard form equation. What I would suggest is leave the most simple term alone. So this first guy, the 5, he is the most simple. So I'm going to leave him alone at the beginning. And I'm going to deal with the imaginary parts. So first I'll distribute in my negatives. So I'll have x minus 1 minus I, and then x minus 1 plus I. And then again, I'm going to leave alone my x minus 5. And then I'm going to distribute out for my other piece. So I'll have x squared minus x plus ix. That was distributing my x here. Next up, I'll distribute my negative 1. That gives me negative x plus 1 minus I. And then lastly, distributing the negative I get negative ix plus I minus I squared. And what should happen here, just like whenever we had the radical solutions, the solutions with the root in it, is the i's should cancel. We have a negative ix, positive ix, those are gone. Positive I, negative I, those are gone. And then lastly, we have the negative I squared. Well, I squared is a negative 1, so this is negative 1, which is going to be a positive 1, right? So let me just rewrite it right below here. X minus 5, then x squared minus x plus 1, and then plus another 1. That last 1 is from there. Now I'm going to pull this over here, and I'm going to combine like terms. So I have x minus 5 as my first binomial. And then combining like terms, I'll have x squared minus 2x plus 2. Lastly, I distribute my x and then my negative 5, and I'll have, actually, you know what? I wouldn't have parentheses, would I? X cubed minus 2x squared plus 2x minus 5x squared plus 10x minus 10. Adding those together, I get x cubed minus 7x squared plus 12x minus 10. And are we supposed to be writing a function? I think we are. Polynomial function f. So we're going to call this guy f of x. So there we go. That's number 38. Next up, we have Descartes' rule of signs. And this is something that I'm going to talk about in class. So for number 39, just number 39. Remind me to talk about that in class so that we can learn about that. All right, again, I want to talk more about number 38. The very first thing we do is we analyze the zeros that they have written down, and we look to see, are there any extra zeros? Because we had this imaginary zero that they wrote, we knew that he had to have a partner, so we wrote his partner down. After that, we write them all in factored form, and then the rest of the problem is just a long multiplication problem. So we just have to multiply them out until we get to our answer over here. All right, that is that section. I know these problems can be intimidating, but always just try to follow the pattern of you first look for how many solutions are there, right? In number 36 and 37, we first looked and we said, well, there are going to be 4 solutions. In both of these, they had 4 solutions. Then we looked to see, can we factor it? And if you can factor it, that's awesome. That makes the problem a whole lot easier. In number 36, we were able to factor. If you cannot factor, then you want to use the rational roots theorem. The rational roots theorem normally makes the problem a little bit longer, but it still works just as well. Remember, when we're doing the rational roots theorem, we normally use a graph in our graphing calculator to help guide our decisions. It would be inappropriate for me to look at the graph and then to jump to my solutions. And it would be wrong for you guys to do that too. On homework, I'm wanting to see that you know how to do the problem by hand. I'm good with us using a graphing calculator to help us get there a little bit faster. That way we don't maybe go by a bad decision in the early. You know, if had I, you know what, let me talk about what I mean by going by a bad decision. All of these roots, we could have typed them all in separately, and I guess there'd only be 8 of them there, so it wouldn't be that terrible. But by looking at the graph, I could jump and say, well, I think it's going to be 2 and 4. And whenever I saw the 2 and the 4, I confirmed, well, those are listed in my possible roots. And then I worked it from there. So again, the graphing calculator can help guide you, but I want to see all the work there by hand so that we know how to do it without the graphing calculator. All right, I've talked enough. That's going to be it for section 6.